George about Calabi applications and
right. First two lectures we spent doing random mathematics, and then we saw in the last lecture that it was actually useful. Things that we learned were useful for group supply application. The tensors that we were looking at yesterday appeared miraculously on the board today. We saw the C tensors and so on, and symmetric. All living in 10 dimensions, but you now know how to compactify that part of the theory down to 4 dimensions if you want to, or 6, or wherever you want to end up, by looking at a product manifold and the internal space, or the small space being compact, and then we learned yesterday how to determine what we get in 4 dimensions through the topology of the die, which was supposed to be small. That was the topology. In fact, that's all we needed. You can see the metric, or any metric structure of the die that was small. Today, however, I want to change the tone a little bit, and I want to talk about supersymmetry. So, the reason for wanting to preserve supersymmetry is that I want to actually have a reason, it may not be a great reason, but it's a reason for why I can control, to some extent, my choice, the manifold, my 10-dimensional manifold, can somehow retain this form. We've been learning that supersymmetry protects things, so that's the attitude that we'll take. And so we're going to take the attitude that the manifold that we're interested in will be such that a certain amount of supersymmetry will be preserved, so we won't break all the supersymmetry. And one of the reasons for that is that basically any solution that you think that you've got from string theory, if it doesn't have supersymmetry, you have no control. Zero control. I won't prove that statement, but it's true. You can pretend that if you have some solution that it stays with you forever in string theory, but it's just not true unless you've got some supersymmetry. So our aim, basically, you get runaway solutions with cosmological constants going on, being huge and so on. So, and I didn't even talk about any of that. So, without any other pretense, I'll just say I want to preserve some supersymmetry. On the other hand, by the time I get down to 4 dimensions, say here, so we'll take an internal space to be some K6. By the time I get there, I know that that's good. By the time I get to here, I know that I don't really want too much supersymmetry because, well, as we said last time, we don't really see it. Or actually, that's not quite true. Whitman once said, well, we see half of it. Which I thought was clever. So the more supersymmetry you've got down on M4, the more explaining you've got to do about how you get rid of the stuff. So what we'll look for is situations where we preserve some supersymmetry, possibly not all. I'll tell you, we'll go through and see how much we can actually preserve in the tip. So what does it mean to preserve some supersymmetry? It means, well, we've got some ground state. It's my ground state. I'm about to do a flip. So now let me call it omega, because calling it 0 makes you think that it's got 0 energy. So Sorry. Let's just call it omega. And then basically what I'm saying is that if I take the supersymmetry transformation of any nice observable, that should be 0 if the vacuum preserves Q. If the vacuum does not preserve, the vacuum is not preserved by Q, so Q on the vacuum is not 0, then this will never be 0, right? There's no good reason for that to be 0. So what we want to do is to be sure that this is true. Now at the classical level, if you're doing quantum field theory, at the classical level, this object is just the transformation you first thought of. That's just the supersymmetry transformation of that guy. So at the classical level, what I'm asking for is D, or delta is my variation. You guys keep calling it Q, so I'll call it Q. Q of my fields are 0. Okay. Now the solution, the gravity solution that I was looking for before was the one where actually basically all the fields are 10 dimensions. We didn't talk about the fields at 10 to get this background. They were all turned off. So solutions where they were all set to 0. So if you look at the did anyone actually write down the supergravity transformation rules? Yeah, maybe. You did go to those lectures, right? So somebody did write down the supersymmetry. Okay, good. So basically what you find is the variation of the bosonic fields go into the fermions times the supersymmetry parameter. Okay? So if I turn my fields off, then the variation of the bosonic fields is 0, because I've turned all the fields off. So if the fermionic fields are 0, well, this is okay. This is looking good. Okay? On the other hand, if I vary the fermions, then I've basically got bosons times supersymmetry parameter and 0. Except there's one field for which this is not true. It's the Rita-Schringer field. So the variation of the Rita-Schringer field, so let me choose some notation which is consistent. Okay, just yeah. This is a vector spinner. And this is not just bosons times parameter plus fermions squared, which it is, by the way, times parameter, but it is actually covariant derivative of the parameter. Everybody else has kind of this form here, I could act. Fermion squared, like this, but except for this guy. So if we want supersymmetry, like this argument, then what I really, really would like to be true is that the covariant derivative of my parameter is 0. To preserve supersymmetry. I haven't told you how much I'm going to preserve. I just want to preserve. Yes,
excuse me, just to be sure, this anti-commutator between the ground state is between Q and
some
Q?
observable. So I could take that to be a fundamental field.
Okay.
Something, some operator in the theory. Now, there's a thing which happens to be true very often. I won't even try to prove that it's true, and that is if you can find solutions to the variation equations for supersymmetry transformations, then you actually have a solution to the equation of motion. So you get something for free. I like things which come for free. So we end up solving equations of motion. I'm not going to really need that, but it's a good thing to keep in mind. It's used very often in superannuals theories in lower dimensions.
Sorry, Josh, can you repeat the argument why you arrived to?
Right. So I want to find a vacuum which is preserved by Q. So in particular, if I just worry about putting in all the fields here that appear in the theory, I want this to be 0. At the classical level, that's the same as asking that the variation of fields is 0. These are the variations of the fields. So the logic is, I don't really even have to tell you precisely what they are. I have a supersymmetry parameter which is an anticommuting variable. Okay? So if this is bosonic, then it has to be anticommuting times my supersymmetry parameter. Otherwise, I don't get something which is bosonic, right? So fermion's the same. This is just the argument, without knowing details. However, we've got one guy which is the gauge field for the gauge symmetry, if you like to use that language for the supersymmetry. It's this chap, the Rita-Schwinger field, and that's why we get the covariant derivative of the parameter that we had in mind. Okay, the spinner. And this is true for, sorry, this is 2A, 2B, type 1, Fred, whatever. They're all like that. Okay?
Could you repeat how you end up solving equations of motion?
No, I didn't tell you how I just said you end up. All right? Just something to keep in the back of your head.
But why did you say that?
Because it's useful in your life. Oh, equations of motion are second order differential equations and nonlinear. Correct? Usually. These guys are all first order, still nonlinear, but first order nonlinear. This is much easier to do. Sorry. Right. So here's our job. We want to solve this equation. Now let me write this equation out and go in detail. You all remember, especially if I could actually find some notation somewhere. Here we go. What this looks like. The covariant derivative of the spinor field, eta, is the normal derivative. Spinor fields, you won't bother you with that, you probably know it anyway, so I'll just, let me put the label back on. Alpha is my spinor label, and then I have my spin connection. Did somebody actually do any of this? Great, he's terrific. Thank you, Nathan. There we are. That's the covariant derivative of the spinor field in a gravitational background. It requires that you have a spin connection. These are the generators of the SON, right? As Nathan pointed out. Sorry, I don't know what notation. I myself keep jumping notation, so let me just use gamma AB. Gamma AB for me is 1/2 gamma A, gamma B, like that. All right. The spin connection can be determined by using an n-bind. So let's say we have dA equals plus having that equation, and knowing that the covariant derivative of V with respect to the Levi-Civita connection else. So that will let you determine this stuff. I've said it before. All right. So what we're looking for is an equation. So we want to solve that equation there. That's not an equation. That's, if we're in 10 dimensions, that's 10 labels there. What's the dimension of my spinner in 10 dimensions? 2 to the 5.
32.
32. So it's 10 times 32. How many equations do I have? Come on, it's breakfast time. Yeah, right. So it's a lot of equations. So we need to think a little bit about how we're going to solve some set of equations like this. Yes?
What's geometrically, what's eta? I don't see it clearly.
Geometrically, what is eta? Eta is a spinner.
Spinner,
Just-
but it's a spinner in 10 dimensions.
Yes.
And it's on a background that is,
No background yet.
okay.
I'll talk about the background in just a minute. At the moment, I'm just intending. Yeah. Thank you. All right. So, I want to solve that equation. Let me show you that you cannot solve it. It's always good to know. Mostly, the only solution, the only solutions are eta equals 0 on arbitrary x 10. And so what I'm really saying to you is that x10 cannot be arbitrary. It has to actually be special before you can actually find solutions to this equation. So the way you go about showing that is you start off by saying, okay, let me consider the curve this. By the way, I still haven't told you what type of spinner. I'll get to that in a tick. This must be true because if that's true for m, it's also true for n. And so that must be true. What happens when you take the commutator of two covariant derivatives?
Translation.
Get the curvature, yes, with the Spanish accent. So this is R, N, sorry. I should have said Chilean. So AB, and things that I call gamma AB, and then eta. And then this curvature tensor is the curvature tensor. It really is the curvature tensor of the spin connection. You should think of the spin. From gauge theories, you know that if I give you a connection, I can always construct the curvature 2 form. This is a connection, happens to have a vector label, and ABs here go over SON, so it's a SON connection, right? And so therefore I should be able to write the curvature 2 form, so in 4 dimensions this would be n, mu, nu, and then just the group labels, the algebra labels right there. And it has exactly the form that you would imagine that it has, which is, actually if I wrote it in differential form notation, you'd probably like it even better. So let me write it like this, which is D.
B.
B. Yes, thank you. So let's clean that up a little bit. Drop the labels so that everybody will accept that I could actually get them right if I tried hard enough. And that is the object which we would write as D and omega n B minus D and m plus the commutator essentially of omega m n as a matrix. It's an AB matrix. So, but this should equal 0. this, whatever the solution is,
Excuse me, you're using, are you using Levi-Civita connection, right?
I haven't used a connection.
Yeah.
I mean, I have used a connection. I've used the spin connection.
Okay, no, because I remember that in the commutator of that such derivative, there must be a contribution from the torsion at the right hand side.
No. Look at this equation here.
Okay.
The right-hand side has no torsion.
Okay.
So what we're really wanting to study is a consistency condition. I mean, after all, this is a first-order differential equation, which we want to solve. We're now getting a consistency condition on that equation. This is the consistency condition. Okay? And already you see that somehow the Riemann tensor is involved in the consistency. So x cannot possibly be arbitrary for a solution. X has to be special. Okay? X has to be special. So we now want to find out how special X has to be to have a solution. Me too. We want to solve this equation. Okay. This equation implies that equation. This is stronger. This is a stronger condition than that one, right? This is just consistency, all right? But nevertheless, if I have a solution to this equation, if I want one, then that object right there should be 0. But that object right there involves the Riemann tensor of X, big manifold. Therefore, whatever the consistency is, it puts conditions on the Riemann tensor, which means that as a metric space, I can't just have anything random. Okay? So I've already told you that mostly the only solutions are e to the equals 0 and arbitrary x. We need a special x. So special x is what we need. Okay. So if I write this, if I use the n-bind to the same bind in this case to move labels up, down, left, right, center, then this equation can be written in a standard way as, I've got space, so I'll put it here, sorry. R, M, N, B, Q times gamma BQ upstairs dot eta is equal to 0, where this is now your favorite Riemann tensor. So now we need to manipulate this thing to learn more about the conditions themselves. So I'm going to introduce the totally antisymmetric rank 3 gamma matrix, or 3 gamma matrices multiplied together, which is this guy. Q, yes, that's right. It's gamma, gamma, P. Notice it's a factor of 3, not 3 factorial. That's because this guy, this is the antisymmetric rank 2 guy, that one right there has a 1 over 2 factorial inside it, so that's where that's it. Okay. So all those things are taken care of. And a little, meaning please try this. So you can count this as homework if you like. Gamma P gamma Q R is simply equal to gamma P Q R minus G R P gamma Q plus G Q gamma R. Remember, we're in a curved manifold, and therefore our gamma matrices satisfy gamma P, gamma Q, the anticommutator is actually 2G you raise and lower now the tangent space labels by the metric. So that's what we've done. So this is the, please do a little bit of algebra. Okay. And so from this, we can deduce, this is a free, oh God, I've relabeled it. So, let me relabel this equation. I've just relabeled. It's the same equation as before, nothing's happened. Except, because I've got this property, what I'll do is I'll multiply by gamma p. Okay? So now multiply this by gamma p. So this implies that we have R, M, N, P, Q, R, gamma p, gamma, Q, R, eta equals 0. And then we use this identity, which you've just proven. Okay? And that identity allows me to write this as follows. Sorry. Hang on, too many labels. Who did that? So I'm just stealing that thing there. Gamma P Q R minus G R P gamma Q, and then plus G P Q gamma R. That dotted in eta equals 0. Okay. Now I need a special identity from that you might remember. The Riemann curvature tensor has the following property that M P Q R plus gamma M Q R P plus, R plus big R M R P Q equals 0. And therefore, this guy here kills that guy there. So what we're left with is essentially R M N gamma N dot eta is 0, and the RMN is equal to R M P N Q G Q. And I've used anti-symmetry to move labels around so that we just get R twice actually. It doesn't matter, this is what we get. So after all those shenanigans, the equation that we really want to solve is that one there. Well, that is definitely much easier to consider than that. So let's get one piece of information from this straight away. Even if we knew nothing, we could multiply this by gamma m, right? Do you agree?
Yeah.
Thank you. So if I multiply that, oh, this is symmetric. Remember, the Ricci tensor has this property. So if I multiply that guy times gamma m, I get Rmn gamma m gamma n eta equals 0. Rmn is symmetric, therefore that's the same as writing this as 1/2 like that. That's GMN. So I end up with R, the Ricci scalar, times eta equals 0. And if the Ricci scalar is not 0, sorry, if eta is not 0, I automatically have that I have a Ricci scalar flat, or Ricci scalar 0 manifold. So the Ricci tensor better be 0. Ricci scalar of x better equal 0. Well, this is a vector equation. Okay, it's a vector spinor equation still, but it's at least a vector equation. I've simplified it further and gotten one condition. However, we can solve that equation. And the way we solve that equation is we simply say, okay, if I had done this for the complex conjugate spinor, right, then I would have ended up with eta bar r m n gamma n is 0 for the complex conjugate spinor. And now I can just bung the two against each other. And so I consider 0, this 0, which is eta bar r m n gamma n. And now I'll just put in a gamma L, and then I'll just put an eta there. And that's still 0 because this part here is 0, yes? Now here we could take the symmetric or the antisymmetric bits. If we put the gamma n on that side, what happens? I get 0. So I can actually just write this. It doesn't cost me anything because I put it on the other side, I get 0. So I now have this equation which says that 0 is equal to eta bar r n l eta equals 0. This is not a spinor, so I can take it out of the dot product. So this implies r m l eta bar dot eta is equal to 0. What do you know about covariant derivatives? Well, one thing you do know about covariant derivatives is that if I've got somebody that transforms the covariant derivative correctly, and then I take its conjugate and form the inner product, then the derivative of that is covariant derivative of the first guy plus your favorite Leibniz rule, covariant derivative of the second guy. Yes? So d m eta bar dot eta is the same as covariant derivative eta bar dot eta plus eta bar covariant eta. What do I know about the covariant derivative of eta? It's 0. So this combination is constant. So yes, the derivative is 0, but eta bar dot eta is constant. So eta bar dot eta is constant. Okay. Now you're home. Because if eta bar dot eta is constant and eta is not 0, this cannot be 0 anywhere. Correct? If that's not 0 anywhere and we come over here, what happens apart from me getting a sore finger?
RML.
Ricci tensor is 0 everywhere. All right? Because if eta bar eta happened to have been 0 in a big part of space-time, then this could have been non-zero somewhere. But that's not the case. These guys, if eta is really not 0 somewhere, it's not 0, that combination is not zero everywhere. Okay? And therefore, we have come into a completely new realm of math, which is we're now interested in Ricci flat manifolds. And these guys are Rn of x is equal to 0. So, your poor little defenseless spinner over there, the one you were wondering about, as long as it's covariantly constant and not zero, can only survive on a manifold which satisfies that condition. Okay? I haven't given you a solution, but I know for sure that if I don't impose that condition, I will not get a solution, except for the obvious one, which is eta equals 0. So, supersymmetry is now dictating something which is not topological about X, it's dictating something which is metric about X. Okay, so before when we were doing Kaluza-Klein, we were just using the topology of the internal manifold to tell us about the physics downstairs. Now we actually need to know something about metric structures. So this is great because if X is Minkowski space times my favorite internal manifold, what can you tell me about the, if I restrict these labels m and n to mu nu of X, this is really just R mu nu is my product metric of m equals 0, and you're not too worried about that. Who's worried?
Okay.
Huh?
Okay.
Okay. Hey! No, remember we're using a product metric on this guy. So if I use mu nu as my labels, then I'm only seeing the metric on the on this chap. So this Minkowski space satisfies, many other spaces satisfy it too, but Minkowski space at least satisfies that equation, right? So we're okay. So one solution for us is that this is really honestly Minkowski. There is no mixed component because we organized that there would be no mixed component because we took the product metric. That is, the thing splits, right? So the only other component that we have to worry about is Rij k equals 0. This is the actual equation which is of interest for us. All right, so now before you start hitting your head against a brick wall, let me tell you something about such spaces. Because K, remember for us, K for us is compact, closed, and in principle could be of any dimension, because these arguments that we just had didn't really rely on 10 dimensions at all, did they? So that could have been any dimension. So now I can tell you what the mathematicians know.
Sorry, I have a question.
Yes, please.
For consistency of to preserve supersymmetry, you have to be in a really flat 4-dimensional manifold, but that implies general relativity that you don't have matter.
This is a background.
But in the 4-dimensional manifold is not the metric you restrict from the background.
This is the. Remember, I'm trying to find a solution on top of which to do the fluctuation. So I'm actually looking for a solution which looks like that. And then on top of it, I want to do perturbations. Right. For example, the. Can you wait for a little while?
Sorry?
can you wait for a little while? Keep the question until I get to perturbations of the metric, if I ever get there. Okay? So what do the mathematicians tell us? Berger did a lot of this, and basically your choices are the following: Ritchie flat. So Ritchie flat. What are the choices? Okay. So you can have UN subgroup of SO2N. I'll explain this in just a tick. You can have an SUN subgroup of SO2N. That's kind of nice. You can have an SPN subgroup of SO4N. And you can have a G2 subgroup of SO7. And you can have a spin 7 subgroup of SO8. These are known as Kähler manifolds. These are Calabi-Yau. Finally, we can stop now. I've said the word Calabi-Yau once. So SPNs are what I would call hyperkähler. Hyperkähler manifolds. This has the fantastic name, as Clifford would say, really creative name, as a G2 manifold. And likewise, this is called the spin 7 manifold. Okay. Now, if this is a subgroup of SO7, this only exists in 7 dimensions. Actually, what I'm saying is not quite true, and I'll correct it just a bit. And this guy is a subset of subgroup of SO8, so that can only live in 8 dimensions. These are the ones, apart from tori. Tori you can have. So a torus of any dimension. They're not here because he excluded them for very good reasons. And symmetric spaces, which are also boring. He excluded those too. Don't worry about those. They don't enter into our discussion. So the stuff that doesn't enter into our discussion is this stuff here. Torus may enter. So what are the possibilities? The possibilities are that I have these things called Kähler manifolds, I have these things called Calabi-Yau manifolds, and if I'm in 10 dimensions or less, then you can see for Calabi-Yau there's not much choice, right? And for hyperkähler, there's definitely not much choice. And of course, these are actually sitting in there, which is quite amazing in itself. So what I'm going to do now is explain what.
Why are you choosing that particular group? Are describing the autonomies?
I started my last sentence with, I'm now going to. Sorry, I'm now going to sorry. So I'm now going to tell you what this is about, but he's already killed the punchline. So, all right, mathematicians. So, thanks. So now I would like to remind you that I lied. So I told you I was lying, and now I'll tell you where I was lying. I said this is impossible to solve. Actually, it's dead easy to solve. Take any curve you like on your manifold X. Here's a curve, here's X, here's a curve. All right. So the motion, the tangent vector, or the motion along the curve, if I call the curve C, it's just C dot. And so I just I ask, well, what happens as I move along the curve? Then the answer is very easy. It's just C dot M. T is the parameter which parameterizes the curve, dm eta. And this should equal 0 because the curve is 0. So I now want to solve that equation. And that equation you know exactly how to solve. It's eta How are we doing for time, by the way?
No, 45.
Yes. So, either at some time t will be the path ordered exponential from 0 to t of the spin connection acting on eta at 0 along the curve. Okay? This is the way Wilson loops or Wilson lines normally arise in gauge theory. So actually, for any curve, we know exactly how to solve this equation. Okie doke. And covariantly constant and have you noticed something about this? Suppose I take a curve, here's x again, here's point, I go trottling around and I come back. Okay, so call that point 0. Doesn't really matter. Let me just call it point P. For point. Okay? So if I start at P and I take a curve and go around, then I get some group element. This is a generator of SON, right? Yeah, thank you. So I get U times eta of the same point P, because that's where I started. Now, I can take any curve I like, so I can do it like that. I'll get, so this, I call this curve 1, so I'll put a 1 there. Here we go. Whoops. Back there, U2, and so on and so forth. Okay? And the statement is that if you take enough paths randomly, then all the U's that you have will fill out SO2n, or SON. Okay? Generically, they'll fill out all the SONs. So that's when you come to the holonomy group, and that's to say that the holonomy group should be SON. Okay. However, because we have this extra condition here, and we want eta not to be 0, it's not possible at all that U covers all of SO2n, or n. Because the only thing that, can't leave anything invariant. I mean, think what's happening. Think of this as some vector in some space. I'm trying to rotate it. So if I use the full rotation group, what happens? It moves. But I'm saying, no, it doesn't. It's not moving. I'm saying it's fixed. But it could be that I'm looking at a rotation group which is a subgroup of the big one. So for example, you know this. Take a vector that's lying along here, and then any rotation in this plane, what does it do to that vector? Nothing. But those rotations are a subgroup of all of the rotations. And therefore, what you're really doing, what you're really telling me with such an equation, is that I'm breaking my group to a subgroup. Berger is telling you, I know exactly which subgroups are allowed. The subgroups which are allowed are these ones. Okay? That's what Berger is telling you. All right? Okay, so that takes care of holonomy. So we have an issue because K, which is 6-dimensional, is supposed to be inside here. It could be a torus, so it could be T6, 6-dimensional torus. It could be something with SU3 holonomy, because that's SO6, right? So it could be something called the Calabi-Yau. It could be the only smaller dimensional guy here is n equals 1, which is SP1. That would give me a, well, differentiable differentiably, the only guy that has that is called K3. So I'll call it K3, and because I want 6 dimensions, I'll just do K3 cross T2. Right? K3 is a 4-dimensional manifold. 4 dimensions. This is 6-dimensional, real. Be careful. Many people call these 3 folds, meaning 3 complex dimensions. Okay, so and that would then have 2 complex dimensions at that point. So basically, I'm going to ignore these 2 guys. You shouldn't. You really ought not to, because if you're starting in 11 dimensions, a much better choice would be this guy, because 11 minus 7 happens to be 4 numerics. So, but we're starting in 10, so for us, a good choice is the Calabi-Yau choice.
What about the Taylor,
Huh?
the first manifold, the Taylor manifold?
Yes. What about the Taylor manifolds? They're not necessarily rich and flat. Thank you. I should have actually written that up there. They're not necessarily Ritchie flat. If they happen to be Ritchie flat, they're one of these 2 in these dimensions. Okay. So, no time for that. No time for that. Okay. I've still got.
Wait, was that statement that any manifold in 6 dimensions has Ritchie flat has to be Calabi-Yau or Taylor?
No. It could be, if it's compact closed and it's Ritchie flat, it'll be either this, or this. Sorry. Okay, so I'm now going to have to do something that I was dreading doing all along, which is talk about spinners. Really talk about spinners. So let me try to talk about spinners. So our group is this group. That's the one that we're actually interested in. And we have gamma matrices which satisfy the correct things. Sometimes I'll write this as 2 eta m n when I'm thinking flat. Okay. Or you can use the n-bind to really make these local Lorentz labels. So in local Lorentz labels, this would be gamma A, gamma B is 2 eta AB. So the generators of SO13 are 1/2 gamma mu, gamma mu. The generators of SO6 are just 1/2 gamma I, gamma J, the same notation that I was using yesterday. Okay. And because we fixed on the top dimension, we have 3 and I is equal to 4 to 9. Okay. So these act independently. That means they actually commute. Check. They commute. And so if a spinner is a spinner of SO1, 9 is a spinner of SO13 and a spinner of SO6. So you can always decompose just as we decomposed forms yesterday, we can always decompose spinners by writing down what they are as spinners of the subgroups. This suggests that there's a tensor product notation for the spinners, and I'll be rather explicit about it. I hope I've chosen a good basis for you. Okay, so the that. Chirality operators. Now, so I need to tell you a little bit about chirality. I'm sorry, I should call the chiral operator in 4 dimensions gamma 5, but that's taken. So I'll call it gamma subscript 4, and it is by definition I, gamma 0, gamma 3. The chirality operator in dimension 6 is minus I, gamma 4 up to gamma 9. That, and it's a very trivial exercise just to use the Clifford algebra to show that gamma 4 squared is the identity matrix, as is gamma 6 squared. And gamma 10, the thing that you would use in 10 dimensions, is just gamma 4, gamma 6, and that 2 squares the identity matrix. Okay, so they're the chiral operators in our theory. So what I'm going to do is going to give you a very explicit, you can do everything without being explicit, but I think it might help you to imagine what's going on by being explicit. So, alright, so the basis I'll take for my gamma i's is gamma 5 tensor gamma I. This is a basis, set up a tick, and gamma mu will be gamma mu tensor 6-dimensional identity matrix. And gamma I is a 6-dimensional gamma matrices that satisfy the usual Clifford algebra, and the gamma mu are 4-dimensional ones. And you can check the following, that remember, when you matrix multiply tensor products, it's lovely because you just actually matrix multiply the entries in the tensor product. So you can actually check everything very explicitly. You can check that this satisfies the 10-dimensional Clifford algebra. I'm sleeping. Okay.
It's not gamma 4. Gamma I.
Sorry?
Gamma 4. You wrote gamma 5.
No, it's a different gamma.
Huh?
So gamma 5 is I, gamma 0, gamma 1, gamma 2, gamma 3.
Okay.
Okay, and gamma 7, which I'll need in just a tick, is minus I, gamma, somebody pick a label, 4 off to gamma 9. Okay? It's just a labeling exercise. Don't. So you can check if you look at these guys and that basis, you find that you get basically gamma nu tensor I6 here. So that really tells you that this is the spin acting on the 4-dimensional spinner, and over here you get the I4 tensor 1/2 gamma I j. So it's a spin. So I chose them so that it decomposes as well as possible. I chose them this morning rather early, so if there's something wrong, please fix it. Okay. Yeah. So now that we know that our spinners really do, we can write our spinners with 2 labels. So our spinner, whatever it was, would have A is equal to 1 through 2. How many? We're in 10 dimensions. How many components does our spinner have? Thank you. 32. But really, I want to write this as eta r alpha bar. The bar on the alpha is because I'm just running out of labels. There's nothing special about it. And then the r is equal to 1 to 4. And the alpha bar just runs from 1 to 8. All right. What's the dimension of the spinner in 6 dimensions? Thank you. So that's the 6 part, that's the 4 part. 4 times 8 is? Right, so you saved me from doing stuff. Now in the tensor product, if I take this matrix and act it on my spinner, all that happens in the tensor matrix stuff is that this stuff here, well, what could it do? So it could only be gamma nu, R S eta S alpha bar. Nothing happens to the alpha bar label, right? Because this is the spin action on the 4-dimensional part. So it only hits the 4-dimensional label. Likewise, 1/2 gamma I, gamma J doesn't know about the 4-dimensional label. It only knows about 6-dimensional spinners. And so what it does is it gives us an alpha bar, beta bar, eta R, beta bar. Okay? The guy, which is ruining everything, well, so far we've only looked at the subgroup. The generator which mixes stuff up is actually gamma mu, gamma I. Right? That's the guy that mixes what I call M by K, right? I'm not interested in him because I want to decompose everything according to M or to K. Okay. One last piece of reminder. This you all got from Nathan's class, I think. So a few more things I want to remind you about. You can always write a 4-dimensional spinner in the following way. You can write, so a 4-dimensional Dirac spinner can be written as a 2-component spinner and a 2-component spinner, like that. The spin group, spin, is of SO3, so spin 4 if you like, is just SL2C. That's the spin group. And so this is a 2-dimensional complex representation of SL2C, and this is the 2-dimensional complex conjugate representation of SL2C. And it's typical in physics literature to keep those two things separated, to cut your brain in half by having dotted and undotted indices. Right. Okay, so this is what we call the 2, and this is what we call the 2 primed. And this is by some choice of gamma 5, this is positive chirality, and this is negative chirality. How do I get a Majorana spinner? Just by staring at that. Well, this is vial upstairs, this is the other vial component downstairs, but a Majorana should be real. And so the way I would get a 4-dimensional spinner with 4 real components is by taking that guy to be the complex conjugate of that guy. So the Majorana spinner in 4 dimensions can be written as psi alpha, psi bar alpha dot, where I mean this is the complex conjugate of that up to an epsilon tensor. But I don't have time. Let's just say it's exactly the complex conjugate, okay? Right. So now we know everything we need to know about 4-dimensional spinners. The other thing we need to know about are 6-dimensional spinners. So course on 6D. So here's the crash course on 6 dimensions. Spin 6 is really SU4. So I'll take positive vial to be a 4, and I'll take negative vial to be the 4 bar. So get rid of that. So, do I still have 20 minutes? Sorry, I'm redoing Nathan's course for one special example. Right. So in 10 dimensions, I have 32 component spinners. Okay. All right. A positive vase spinner in 10 dimensions has how many components? 16. So it's 16. So a positive vase spinner, which I'll write as 16 plus, just so you know it's the positive vase spinner, has got 16 components, and they are complex. All right. So they're all complex components. So 16 plus I can write as a 2,4 plus a 2 prime 4 bar. Why? Because the only way that gamma 10 acting on this could give me plus 1 is if gamma 6 gives me plus 1 and gamma 4 gives me plus 1. And this is a plus 1 spinner and that's a plus 1 spinner, right? So that's fine. Or gamma 6 gives me minus 1 and gamma 4 gives me minus 1. And there we go. That's the 4 bar and the 2 prime by the table over there. So my decomposition of my spinners, my 16, is to have 2 complex, 4 complex, 2 complex, 4 complex. This is 8 complex. 8 complex is, help me here, I can't do arithmetic. So this is 16 complex, right? Correct. So how do I know that this is correct? Well, I told you just a minute ago that my spinner in 10 dimensions is a spinner in 4 and a spinner in 6. I gave you a decomposition where everything sits on one side and everything sits on the other side. So I was able to write it like that. So if I forget that, I have a 4-dimensional spinner which breaks into its vial components. If I forget that, I have a 6-dimensional spinner which breaks into its vial components. I have this. Okay? Sorry, this is a very quick and nasty way of doing things. So 16 minus, well, I need something which is odd chirality. So one way to get that is to have plus 1 and then minus 1, or minus 1 and then plus 1. Okay. And I've lost the page I was on. Right. So in 10 dimensions, I can have what is known as a Majorana vial spinner. So here's my vial spinner. There it is. How do I make it Majorana vial? What's the Majorana condition? Well, I know what the Majorana condition is in 4 dimensions. This really is the complex conjugate of that. It's the same in 6. So I take this to honestly be the complex conjugate of that, and I take that to honestly be the complex conjugate of that, and then I've got a reality condition. So I have a Majorana spinner. So, with abusive notation, 16 Majorana plus would be the 2,4 plus 2 prime 4 bar, but thought of as the bar of the 2,4. So this is an abusive notation. You're supposed to understand that whatever I put in here, it is actually the complex conjugate of that thing there. And likewise, the 16m minus is the same thing. Just that thing. Okay? All right. Let's get to work. So I'm actually only interested in the part which is on K, because it was K which was the covariant derivative. So the covariant derivative dm dot eta equals 0. This splits neatly into the covariant derivative in 4 dimensions, because if there's this split in the metric, there's a split in the spin connection, therefore, okay? And di eta equals 0. These don't mix. This covariant derivative sees eta as a 4-dimensional spinner. This covariant derivative sees eta as a 6-dimensional spinner, okay? Because what is in the covariant derivative is gamma AB. Gamma, well, just rubbed it out. But the gamma ABs split nicely in this tensor product, right? They don't mix. So here I only see the 4-dimensional part of it. The 6-dimensional part's going along for the ride. If I'm in flat Minkowski space, the spin connection is 0. Take it to be 0. This covariant derivative becomes d mu eta rs is 0. Alpha bar equals 0. On the other hand, this guy is still di eta r alpha bar plus some matrix alpha bar beta bar eta r beta bar 0. Because the spin connection in the 6-dimensional part only knows about the 6-dimensional part of the spinner, so it can only be of this form. Okay? So we're looking for guys which are constant in Minkowski space that satisfy the covariant condition over here. R, in this equation, is just hanging around for the ride. It does not enter into the equation. So we can just ignore it for the moment. Just concentrate on the 6-dimensional spinners. Okay. So in 6 dimensions, I'm looking for a solution to di, and I'll call it epsilon equals 0. That's what I'm trying to solve. And from the argument that I gave you before, what we're looking at is a solution to the equation u dot epsilon, where u is an element of in general. In 6 dimensions, well, let's have a think. So if I really have a solution, say one, here's a solution, all right? Then I can use an SU4 transformation. This is a 4 of SU4. I can use an SU4 transformation to move me somewhere. It's a 4-dimensional vector, so a component vector, and I can just move it to the bottom. So I'll say, well, okay, here we go. I have 0, 0, 0, epsilon 1. There's my spinner, supposedly. If I have exactly one solution, you can ask yourselves, how do I solve this equation? After all, that's the problem that we're facing. And the answer is, well, any u, which is of the form u SU4, SU3, 1, 0, 0, acting on epsilon, is epsilon. So if there is exactly one solution, then the group which preserves the symmetry, right, is SU3. So with one solution, SU3 holonomy. What would happen if there were two solutions? Well, one solution. What would happen if there were two solutions? Well, the first one I could use SU4 and put it here. Right? The second one I could use SU3 because it doesn't move this one. SU3 leaves this invariant. I could use SU3 and move it partially into this, which is fine. That's some linear combination of a solution, and into this slot here. So if I have two solutions, I can always write this as 0, 0, epsilon 2, epsilon 1, the way I've been writing it, like that, two solutions. What's the group which preserves that? It's SU2. The group which preserves that are the elements of SU4, which can be written as elements of SU2. It's the 2 by 2 identity matrix down here. Like that. And I'll let you figure out what happens with more solutions. More. All right. So, just by presuming that there is a solution, we see straight away what's happening with the holonomy. Right. Now that we've got that under control, another thing that we need to do is to say, I'm going to consider one solution. Why am I interested in one solution? Because remember, the more solutions I have, the more supersymmetries I have in 4 dimensions. Right? We're looking for solutions which preserve supersymmetry. The more solutions, the more supersymmetry. So I want to look at the best possible case where I essentially just have one. Well, essentially what that means is that if I have this solution, I also have the complex conjugate solution. So I also have the complex conjugate spinor solution, which is that one, right? The 4 bar, if you like. Okay. So if I insist that my holonomy is, so let me say it explicitly. I insist K as SU3 holonomy, and not some subgroup of it. SU2 is a subgroup of SU3. I would have more solutions. So I insist that I have SU3, and therefore I have exactly one spinor, this one, and I have its complex conjugate over there like that. 10 minutes. All right. So that's great. Suppose I want, all we have to do now is we've broken everything into little bits. We've worked out what's going on in 4, we've worked out what's going on in 6, and now we just repackage the whole thing into something that lives in 10 dimensions. Okay, so that our job now is just to finish. Just stick it all together and then see what it tells us. So we do that. So I want to create the 16 m plus. How do I get the 16 m plus? Well, from the discussion over there, we needed the 2, we needed the 4. To that we added what we call the 2-4 bar. Okay? Now, if the 4 spinor really is this, and this, and the 4 bar is really this, then these spinors only have one component. Okay? So this spinor, whatever it is, my eta, in tensor product notation, this one, will be a 2, remember I haven't touched the R label, times epsilon plus a 2 prime times epsilon bar, where this is really the complex conjugate of that, otherwise it won't be Majorana. So if I insist, sorry I should have said that, if I want eta to be a Majorana plus spinor, then it better be like this. This only has one component, so this has 2 complex components times a complex number, which is 2 complex numbers, right? And this is just the complex conjugate of that. So if I've got 2 complex numbers, how many real components do I have? 4. So as far as 4 dimensions is concerned, what is this? 4 real components. Huh? Majorana. Thank you. Did you say that? Oh, okay, he was right. So this is a Majorana spinor. 4 real components. That's what we take something and we add its complex conjugate. This something is a very special spinor. It's not the most general spinor. There are lots of zeros here. Okay? So this is actually really a 2 plus 2 primed, which is this. So we have a 4-dimensional Majorana spinor, and the smallest amount of supersymmetry that we can have in 4 dimensions is n equals 1. And if I have n equals 1 supersymmetry in 4 dimensions, what is the parameter? It's a Majorana spinor. Here it is. Okay, so this leads us to, if this is what we took at the start, this leads us to that. Okay. All right. So, but in type 2A theory, so I need to tell you, how much time do I have? 5 minutes. Okay, so but in type 2A theory, I don't have just a left-handed Majorana, I have a left-handed Majorana plus a, that's right, a right-handed Majorana. I don't know if you said that. So, if I do that, one way to package everything is to get symmetry, is to get a, so this would be what you would call a type 1. So if I was looking at 2A, then eta is actually supposed to be supersymmetry at the top of the scale would have me an m plus plus a 16 m minus. That is to say that it is a 32 component real spinor. Okay? And it's neither left-handed nor right-handed, or possibly more correctly, it is a bit of both. And so you would actually just get both of them. Okay. The type 2A, the type 2A would give us in 2-dimensional notation. Alright, that's not good. Okay, so do I want to write the spin? Yes, okay. So the charge of this would be a 2 plus a 2 prime minus. It's charged. How can I tell what the charge is? Well, I could have put it here. You could also do it. You could also figure out the U1 charge of that guy by just looking at how you can stick in a charge here, right? So actually check the charge. But if this is the complex conjugate of that, then if this has got plus charge, that must have minus charge. If I add this guy to it, I actually have exactly the opposite, which is the 2 minus plus the 2 prime plus. So that's symmetric. The 2B is 2 copies of the same gadget. So what you end up with is just 2. Okay, so all right, 2 copies of one of them. So it's handed, if you like, charged. All right. This was supposed to take the first 10 minutes of today. In the last minus 10 minutes. I hope that's okay. That was just to show you that you can actually deal with the spinners. It's not that hard. You just needed to know some math theorems, which thankfully somebody did and told us about. And then it's just a question of just writing everything out and seeing what you get. Okay, so it's not really difficult. It's just messy. It's really messy. With spinners, I think it's a well-known fact that you should only ever consider spinners in the privacy of your own bathroom. That's it. Nowhere else. In public, it's terrible. You're bound to get it wrong. I'm sure I've done something wrong. So, okay. So in a sense, all of this stuff, the Kaluza-Klein, we've managed to talk about how to handle the differential forms which appear in the higher dimensions. We've learned how to handle the supersymmetry that comes from the higher dimensions. It's no surprise that if you follow the Dirac equation around and you do exactly what I did for the, sorry if I have the Dirac equation in 10 dimensions, d/4 plus d/k acting on my spinner is 0. If I scale this to infinity, shrink it, as we did before, we end up looking for solutions to this equation, well, actually, roughly. And then you can write this out in eigenmodes of the 0 spinners of the spinners on K. That requires another piece of technology, which usually goes by the name of the index theorem. We don't have time, but you can imagine, without even knowing anything about that, that the same thing that we did for differential forms, if you really wanted to, you could do for spinners, and you could just calculate everything for yourselves. It's exactly the same story, it's just a different field. Okay? Same. The one thing which is really, really different is the metric. So we have the metric, which we started off life by saying, well, I want G mu nu, and I want Gij, and I do not want to have my background, so this comes back to your question. I don't want to have G mu I. All right? So I'm trying to solve everything on the background, which is a product metric, and I've really taken a product metric. So what you can ask is, well, suppose I just look at perturbations around these, so we linearize around it. So then I can ask, well, how about G mu nu plus H mu nu, Gij plus Hij, and then basically H mu I, because there was a 0 sitting around. So from the point of view, I'm going to take a very cheeky and quick way out of not having to answer a question, and that is from the point of view of 4 dimensions, I just have a lot of gadgets which are vectors. But these vectors aren't really just vectors, because the 10-dimensional theory was invariant under general coordinate transformations. So these vectors are vectors of a symmetry, even in 4 dimensions. Now, how many of them can I have? Well, I could have that many of them, whatever that many of them means. But let's change the picture a little bit and just do it like this. Let's concentrate on the I. For every mu, I've got a vector. And for reasons similar to the discussion that we had with forms, these guys are actually counted by B1 of K. The reason is a little bit more long-winded, but it's true. These are also counted by B1 of K. Our SU3 holonomy manifold cannot have non-zero B1. It's just a fact of life, because if it was true, I could find more invariants, which would imply that it wasn't SU3 holonomy. So just accept it for the moment. B1 of K for a special holonomy, Calabi-Yau, which has SU3 holonomy, really SU3 holonomy, has B1 of k equals 0, I don't see these. Okay? But that still leaves me with these guys, and this is important because the thing that we've understood about k is that it has to be Ricci flat. So to be fair, what we really need to solve is the equation that the combined thing is Ricci flat, given that the metric I started with is Ricci flat, because I don't want to do a perturbation which takes me away from the conditions that I had. And this implies conditions on H, which you can turn into conditions on Dolbeau cohomology, which we didn't talk about, so I apologize. But you can actually solve for that. You can figure out exactly how many such perturbations there are. As far as you're concerned in M, such perturbations have no vector labels in M on space-time, and therefore they're scalars. And the number of solutions gauge, well, general coordinate invariant solutions to this equation for H are the number of scalars that you will see in 4 dimensions. A little bit more complicated than what we did with the differential forms, but basically that's all there is to it. And I'm tired.
Is there some questions for Josh?
Yeah, in order to derive this flat solution, you start with classical and then what we consider you have modes. So I would guess that you just
So this is the low energy effective theory. I mean, the massive states, is that what you're worried about?
I'm worried about the practical conditions about the manifold because people usually work.
Yeah, so people have calculated corrections to this, and they still find it Ricci flat manifold. So yeah, people are worried. I don't know how others
I would guess that the answer is similar to you just noticed at the end because that's not.
Yeah, but it's something you have to check to be sure that it is of the type. In fact, so you have to do the calculations. People have done those, one loop, and then they see that they can.
So far, you always have fog space, fog manifold.
No, it's as complicated as it gets. Yeah, no. The first Benny number can be 0, but you know, it's, the second Benny number can be outrageously huge. First of all, there is no single clavier. There are untold numbers of claviers. And they're complicated. They're very complicated. I just said that B1 is 0. I can say Phi1, for example, is 0. I can say that. I didn't, yeah, I mean, no. No. Waltz. Keep an eye out on Joyce's books. Every time he writes a book, he shows you how to create more of them. So maybe in one of the, you know, his 10th book, he'll finally tell you how to do it.
What is the book?
Joyce's book by Dominic Joyce. He has 2 books now. Special polynomial manifolds. He's the guy who keeps creating them, and I guess the physicists are the ones who keep using them, so he keeps creating more. I think it's a game he's playing to see if he can create stuff we can't use. He's losing at the moment.
Okay, please let's think again now.